All right, so here's the second part of the optimization lesson and last lesson in this big unit. Essentially, I'm just going to go through 3 more problems involving optimization. These will definitely be more involved. Quite often we'll find the hardest part is, in fact, very often the hardest part has nothing to do with differentiating directly. It's determining what function to differentiate, or getting into a form that we can differentiate with relative ease. The actual differentiating part is quite often very quick. And so here's 3 different examples of problems. And so the first one is I have a parabola, y equals x squared, and I have this point at 0, 1, right there. I want to find the point or points on the curve that are closest to this point 0, 1. So for example, I can just see, that is not, that point there that I've just highlighted in blue is not the closest point to 0, 1, because I can tell that definitely this point is closer. But where is the closest point, right, or points? This is a symmetrical shape, so maybe there's more than one. I don't think it's this point right here at 0, 0, because just visually, this distance here looks shorter. That said, we can figure out where that point is without making any guesses, and I want to find the exact coordinates of where that point is. Okay, so that's the problem. Next, I need to, what I want to do is I want to minimize the distance between this point 0, 1 and some point on the curve. So how do we find the distance between 2 points? Well, we can really use the Pythagorean Theorem. So let me talk about that. So if I want to find the distance between any 2 points, so I'm just going to draw, here's a point, and here's a point. And I'll call this point here x1, y1. I'll call this point here x2, y2. So if I want to find the distance between them, that implies the straight line distance. And like I commented, we can use the Pythagorean Theorem to find the straight line distance if we imagine there being a right triangle. And the distance across the bottom, that's the difference between my x coordinates, and the height of this triangle is the difference between my y coordinates. And so the hypotenuse is the square root of the part highlighted in yellow squared plus the part highlighted in blue squared. So this distance here, so I'll write that up. Try to be a little bit neat here. These questions are going to probably take us a fair number of steps. So using the Pythagorean Theorem, the distance is going to equal the square root of x2 minus x1 all squared plus y2 minus y1 all squared. And this is a formula you may have seen before. It used to be part of Math 10 years ago. They removed it years ago. It's really just the Pythagorean Theorem, right? The distance in the bottom squared plus the distance vertically squared, and the square root of that will be the total distance. All right, so for this particular point, I know, I have x1, y1, x2, y2. I know one of them is 0, 1. One of them is not variable. I'm trying to find the shortest distance from this point, 0, 1, to some point on the curve. Right? The point on the curve is variable. Right? Call that x, y. The point of highlighted in green is 0, 1. So I just need to pick, if I want to use this formula, I just need to pick, I'll call x2, y2, 0, and 1. Because I need to pick one of them. It doesn't really matter. So I could say distance equals the square root of 0 minus x all squared plus 0 minus y all squared. Oh, not 0, sorry, 1. It doesn't matter which one I call x and y. Again, x and y represent some point on that curve. That point is variable. The 0, 1 is not. So I can clean this up a bit. I might as well write this as distance equals the square root of x squared plus 1 minus. Now at this point, this y here, I'll write it in red. If I keep leaving it as a y, my distance function will continue to have 2 variables. I want just one variable in my distance function, because to differentiate something, I need to differentiate with just one variable, at least the level we're at right now. So I need to do something with either the x or the y. It's actually pretty easy for me to replace that y in terms of x, because remember that x and y you see in that radical there represent some point on the curve y equals x squared. literally, y equals x squared. So everywhere I see a y, I can replace it with x squared. There we go. That was actually quite nice. So now let's clean this up. Notice I haven't done any differentiating yet. Expand this binomial. Plus, yeah, I'm all good, just making sure. And so combine like terms. I get x to the power of 4 minus x squared plus 1. Okay, so this function here, this is what I want to minimize, sorry. However, I can make this easier. But this is the function, the distance. This is now distance as a function of x, and x can be any point on that curve. So I want to minimize this. However, keep in mind, if I want to minimize this radical function, really all I really want to minimize is this polynomial function. This, if altogether this whole square root will be at its smallest when the the fourth degree polynomial there is at its smallest. So really, if I'm trying to minimize this distance, I really just need to minimize that fourth degree polynomial, which is significantly easier. We've seen how easy it is to differentiate just a simple polynomial. So while this is the function I'm trying to minimize, to do that, all I really need to do is minimize x to the power of 4 minus x to the power of 2 plus 1. This is easier to minimize. When I say much easier, to be honest, differentiating the function above the radical is relatively easy. Use a chain rule, it's pretty quick. But making that derivative equal 0 gets messier. Whereas, looking at this, differentiating and making e equal 0 are very, very quick. All right, so now I'm actually going to start differentiating, and it'll take me about a second. So d prime is equal to 4x cubed minus 2x. And so now I can make this equal 0. So 0 equals 4x cubed minus 2x. And solve for x. Keep in mind, I have a cubic polynomial here, but I have a greatest common factor of actually 2x I can take out. And I have 2x squared minus 1. Looking for critical numbers. There is a critical number here when x is 0. However, I know that's not the point I want, and I'll talk about why in a bit. I mean, I've already mentioned, actually, I could just tell by looking at it, when x is 0, I know that distance I can see is longer than that distance over there, for example. But it's not a meaningless point. Okay, that is a critical point. But the point I really care about is right here. From here, I can see that x equals plus or minus root 1/2, or plus or minus 1 over root 2. Which means if I look back at so there's 3 critical points. But if I look back at this graph, in terms of x, these critical points, one critical point's at 0, one's over here somewhere, one's symmetrically over here somewhere. And now I know where those coordinates are. This is minus 1 over root 2. This is plus 1 over root 2. And so I can see now the exact x coordinates of my 2 shortest points. I know those are shorter than this point here, just visually by looking at it. If I'm not sure, I could just plug these coordinates back into my distance formula, and I'll get a longer value for at 0, 0. But I don't need to do that. I can just see that here. So what I can see here is that these are my absolute minimums. There's a tie. There's 2 of them. This is a local max. So essentially, I can just see here that as I make my way down, the distance gets shorter, shorter, shorter. This is the shortest point right here. Then distances get a little bit longer. That's the longest distance in that little area. And the distances get shorter again. Here's another shortest point, and then the distances get longer forever. There is no absolute maximum. So let's just kind of formalize all that and finish the question. So my critical points, or critical numbers, are x equals 0, which is a local max, and x equals plus or minus 1 over root 2, which are both local mins and actually absolute mins. And so lastly, I believe the question did ask for the actual point, the coordinates. So I have the x coordinates. So if I want to find the y coordinates, it's pretty easy. Just take those x coordinates and plug them into y equals x squared. So y equals x squared right here. So therefore y equals plus or minus 1 over root 2 all squared, which doesn't matter if it's plus or minus, is a half. So therefore now to formalize the answer, the closest points are at plus or minus 1 over root 2 for the x and 1/2 for the y. Okay, so notice before I move on, definitely a bit more involved in the questions I had from the last lesson, but really, what was the only part here that required anything from this course in terms of differentiating? It was just this step. You know, this step from here to here is differentiating and understanding why we make it equal 0. The actual rest of it is all, you know, it's not easy, but it's not actually stuff you learn directly in this course. Okay, and that's why these problems are difficult, is that they draw upon so many different things, or they can draw upon so many different things. All right, so what I have here is an ellipse, and here's the equation of the ellipse. You can see x squared over 25 plus y squared over 9 equals 1. I want to find the maximum area of a rectangle that can be inscribed in here. So let me just kind of sketch a little rectangle. So for example, here's one possible rectangle. I want to maximize that area, right? And there's many possible rectangles I could draw. Okay. To do that, I want to simplify this down. I want to focus on just one little rectangle here, and then realize the area will be the maximum. You know, the maximum area I can find of a whole rectangle will be that times 4. So let's look at this part. How do I want to set this up? Well, this point here, x comma y, which is both one of the vertices of that rectangle and a point on the ellipse, also can represent the area of this part I've highlighted in yellow, the x coordinate times the y coordinate. As long as we're dealing in the first quadrant, those are both going to be positive, and that'll be the exact same as that area. And so that's how I'm going to set this up. I'm going to set up, I'm going to focus on really maximizing this rectangle by setting it up like this, where I have 4 rectangles, all the same as x times y. So area of the rectangle is going to be the same as a equals 4x times, now I'm going to write y in red for a moment, because again, this area function, this is what I'm trying to eventually maximize, but I don't want to have 2 variables in it. So I need to take either the x or the y and write them in terms of the other. In this case, it doesn't really matter which one I do. I'm going to replace y in terms of x, because if I look right here, I have, you know, that's the equation that tells me how x and y are related to one another. I can solve for x or y with the same amount of work. It's a little bit too much to do just in my head, but you know, I'm going to pick one. So I'm going to solve for y here. So let's take my equation up here. The first thing I would do if I solve for y is multiply everything by 9. Well, I'd bring x squared minus 25 over, so x squared plus 25 over, so subtract x squared over 25, and then multiply everything by 9. That was going to be my first step. Okay. At this point, there's lots of things I could do. I mean, I could just square root the whole thing right now and shove it back into their function, but then I'll make my life needlessly messy. If I just right now square root that and put that right here, and then try to differentiate that, I'll get a really messy function to differentiate, needlessly messy, and then trying to find the critical points will get needlessly complex. And this happens a lot where we basically just get impatient. We make our life significantly harder. So I want to clean this up as much as I can. And constants are great things to get out. Right now there's a constant of 9. And the more constants we can kind of factor out, the easier it is to differentiate. So what I want to do is first I want to find a common denominator of 25. And if I do that, I can now, that denominator of 25, I can write as a coefficient in the front. Right. And this is all equals y squared. That's it. That looks a lot nicer to me than what I started with, especially when I square root this now. And while there are technically two possibilities when I squared x and y, I already said I'm just thinking about the first quadrant, so that my x and y are always positive. So I don't need to worry about the negative version, so I'm not going to write down the plus or minus. When I square root all of this, I get just 3/5 times the square root of 25 minus x squared. And if I compare that to just square rooting that, I think it's more pleasant to deal with. So I'm going to take that there and write it in my area function. All right, so again now, I do have a function in terms of just x I could differentiate, but that's a poor idea right now. Let's clean this up a bit. For example, those constants, or those coefficients or factors of 4 and 3/5, I might as well put those together. And while I'm at it, I could again differentiate this right now, but it's relatively easy for me to take this x and write it inside this radical. If I just change x to x squared and then multiply it in. So again, I can kind of imagine this being the same as that, and then multiplying that in. Because then I don't have to, otherwise I'd have to use the product rule when I differentiate. And again, notice what I'm doing right now, this is grade 10 math in many ways. You work, or grade 11 math, working with radicals. Notice I haven't done any differentiating yet. And so this is what I'm going to differentiate. That said, to differentiate this, I'd rather have that radical written as a power, so I'm going to do this. All right, so that's what I'm going to differentiate. Now I got into a form that I know I can differentiate quite quickly. All right, although it will be a bit definitely messier than what I had in the previous question. So a prime, well, 12/5, constants are great. Use the power rule. So first, actually, I'll multiply. I'm going to bring over the 1/2, so I'll just write this as 12/10 right now. Save myself a bit of time. The inside part stays the same. Multiply by the derivative of the inside function. All right, so this is my derivative, but remember, we're trying to use this derivative, so I'm trying to find the critical points. Now, right now, just by looking at this, I know I don't have to worry about this part here, because all of this is the power of negative 1/2, which means all of that is I'm dividing by all this and rooting it. That's not going to lead me to a derivative equal to 0. I want to make my critical point. I want to find critical points where it equals 0. Again, like I mentioned before, finding critical points where your derivative does not exist will never lead to an optimal value. So I just need to focus actually on this part right here. This is my numerator. I want to make this equal to 0. OK, now this actually is quite similar to before. Take out a factor of 2x. Again, looking at this here, I have a critical number when x equals 0, but I don't care about that. When x is 0, notice remember what x stands for. That means my x coordinate is right here, which means my y coordinate, I can see where it is, which means I have an area of 0, because that means I have a rectangle like that. Okay, that is a critical point, but I know I don't have to deal with it at all, because that's not definitely going to be the maximum area, so I don't care about that anymore. It's what's inside the brackets here that's going to be more useful to me. This is going to lead to my values that are important to me. And actually here I should say x equals plus or minus. Well, I could say, hold on. I'll write down plus or minus for a moment, because x is a coordinate. So when I square it, I get 5 over root 2. But again, I've already commented that I'm focusing on just this first quadrant, and then I can just multiply everything by 4. So because I know I'm dealing with the first quadrant, I can really just not worry about that plus or minus. So I'm just going to deal with x equals 5 over root 2. So that tells me the x coordinate that I kind of sketched out for my little visual up here. I now know the x coordinate up here for the maximum distance is 5 over root 2. So to find the area, well, I need to find the y coordinate. and that should be pretty straightforward because right here I have an equation I've already set up that tells me how to find a y coordinate if I know x. So I'm now going to take the x coordinate and put it into that equation right there. At this point, clean this up a bit, we get 25 over 2 exactly inside the radical, which when you square it is the same as 3/5 times 5 over root 2. And simplify all that down, the 5's cancel out. You get 3 over root 2 is my y coordinate. And so now I can find the maximum area. The maximum area. Remember, I said area equals 4 times xy. So in this case, 4 times 5 over root 2 times 3 over root 2. Clean that all up, you get 60 over 2, or exactly 30 square units. All right, so again, definitely more involved than the last day. But again, most of my work was not differentiating. And so here's the last question. I have this cylinder inscribed inside a cone. And I want to, and some dimensions of the cone. I know the distance across the bottom from here to here is 4 centimeters. And the height from here to here is 8 centimeters. Okay, that's the dimensions of the cone. That's constant. The cylinder is variable inside there, and we want to find the maximum volume. So what is the, I think the question is asking, yeah, what is the actual volume? This, I could ask, what are the dimensions of it, but what is the volume of the largest cylinder that can fit inside here? Okay, so let's remember the first equation for the volume of a cylinder, because I'm trying to maximize the volume of a cylinder. So, volume of a cylinder is same as pi r squared height. Nice and simple. Okay, but again, that's what I'm trying to maximize, but I have two variables. So I need to think how are r and h related to one another. I need to either write r in terms of h or h in terms of r. Well, if I look at this, there's a few ways of setting it up, but one way I'm going to use is similar triangles, because regardless what this what the cylinder looks like inside here, I can see the radius of the cylinder is going to be proportional to the radius of the cone. And the height of the cone is going to be proportional to the height of this empty space right here. Right? This triangle here is similar to this triangle here. So that's the proportion I see. And no matter how I draw this cylinder, if I draw something like this, a really stout one, I'll still see that relationship is true. And so the proportion between the height between 4 and 8 is proportional to radius and not the height of the cylinder, because the height of the cylinder is this. So this little distance from here to here is 8 minus h. And so now if you look at my diagram, I can say 4 over 8 is proportional to r over 8 minus h. Those are always going to be proportional to each other. And there's other ways I could set it up, but that's what I'm going to write down. So again, using similar triangles. So I'll write it down here. 4 over 8, I'll be nice and colorful, is proportional to the radius of the cylinder divided by not the height of the cylinder, 8 minus the height of the cylinder. All right, so now I can solve for r, I can solve for h. I'm going to solve for h just because it's just h in the equation, it's not h squared. And so if I quickly solve for h here, I can simplify this down to 1/2 equals r over 8 minus h. Solve for h. I'll multiply both sides. I'll multiply both sides by 2 and 8 minus h, or cross multiply, actually, same thing. So h must be equivalent to 8 minus 2r. And I think the hardest part of this question is for sure done. And there's other ways. I will say, another way I've thought about this before in the past is to imagine this being kind of a linear function on the xy coordinate plane, or maybe this is 0, 0. I mean, there's other ways, but in the end, most of our work is trying to figure out how are the radius and the height of the cylinder related to one another, since they're constrained inside this cone. And so now I can go back to my volume function and rewrite it as pi times r squared times 8 minus 2r. OK, and I could differentiate this right now, but I'm going to differentiate this, and I want to oh, hold on. I got someone. Oh, we're going to have a little exciting intermission. I have to talk to someone at the door. Hold on. Well, that was exciting. Probably more exciting than the entire video. All right, so let me clean this up a bit. If I differentiate it right now, I have to use the product rule kind of needlessly. So I'm going to distribute the r squared, for example. And as well, I mean, while this is already a lot nicer, I can see a common factor of 2 I can take out from inside that factor of ar squared minus 2r cubed. And again, the more factors and constants I can take out, the easier my work is. There you go. This is the function I'm going to maximize. Helps if I can spell. And so when I differentiate this, it's really because I've chosen to clean it up a bit. I don't have to use chain rule, product rule, anything. V prime will be 2 pi times the derivative of this. And so now my critical numbers are where what you see highlighted in blue will equal 0. Which, take out a common factor of r, is when r equals 0, which is clearly not going to be a point that's going to lead to the maximum maximum volume, or when r equals 8/3. That's the one I want. So this is my minimum. This is what I care about. This is my max. So now let's find the total volume, or I'll find the height as well. So I already know that height now of the cylinder is equivalent to 8 minus 2r. So I might as well find this. Which, if you clean it up a bit, you get 8/3. There's your height. So the maximum, the best radius is 8/3. The best height is also 8/3, same number. And so now let's find that maximum volume. So I'll say don't forget maximum volume. Volume is always the same as pi times r squared times h. Well, these are all the same. It's 8/3 squared times another 8/3. So pi times 8/3 cubed. And I'll say that's a great answer. But 8 to the power of 3 is 512. So 512 pi over 27 cubic centimeters. But again, that answer before was great as well. Notice, as I said at the beginning of this video, our challenges will most likely not be the actual differentiating part. It's getting to a function that we can differentiate with relative ease and also use. That's it.